Okay, so today I'm going to mainly talk about my simulator RISIM and a bit of control work using RISIM. So first of all, I probably, if you know from me from ETH, I moved to KAIST in March. So I'm settling down here. Yeah, and yeah, we have a new lab called RILab, which is a part of Hugo Lab. And we do a lot of Lego robotics, physics simulation, learning-based control. So if you're looking for postdoc position, PhD position, feel free to apply. So this is a kind of problem I want to solve. And you can see that for this kind of motion, you need really dynamic motion. First, you have to plan the trajectory. Then you identify where to step. Then you execute the motion. And this motion will be very dynamic. And if you have dynamic motion coupled with a planning problem, and this is very challenging because you're planning usually use a simple model, but then you need to have a dynamic motions in order to cross that the stepping stones, right? So this is I don't think anyone ever showed or demonstrated a controller like this, and this is a kind of problem that I want to solve. So of course, I want to do it using reinforcement learning, if you know my research. So there have been a lot of success in reinforcement learning applied to Lego robotics. So on the left top, you can see my last year's publication where we did control of Lego robot animal. So here we can just kick the robot, and so basically everything is controlled by a single neural network. We get input as a state of the robot, the output actually direct actual command, and we can create motions like this. I'm going to show more videos later, but yeah. So, but the point of this slide is not just my work, but I want to say that there were tons of success in reinforcement learning, also from like agility robotics, Google Brain, and so on. And it's becoming a promising approach. So before it was more like a gimmick when I started my PhD, but now I think we have a really nice tool to work with. But I think many people have preconception that reinforcement learning is very laborious, require laborious tuning, and very time consuming. So I made an example. So this example, actually, you can download it from risim.com. So it has a link to the GitHub. And so here, this is the initial policy, right? So it's controlled by a randomly initialized neural network. Of course, then you will do something random, it hits itself and then resets to the default position, just repeating itself. So of course, we don't want that. So that was the initial policy. After 2 minutes training, 2 minutes of training, so here we use the full robot dynamics. And after 2 minutes of training, which corresponds to about 200 iterations of PPO, we see animal running like this. It's not like the optimal, I would say, but it's stable and it's running. And after four minutes of training, after about 400 iterations of PPO, we see quite fast locomotion behavior. So quite periodic, and I would say, so this is also using the joint torque limit. So within the limits is, I would say, it's near the optimal. So the code to produce this was 130 lines. And there was only 2 different cost terms. One that rewards the forward velocity, and one that penalizes the joint torque use. Since we are only interested in the ratio between them, basically you only have to tune one parameter to get this. Right? And of course, if you start from 0 torque penalization, then you slightly increase, and you just pick the motion that you like. You stop when you get the motion that you like. Okay, I also put like really work on rough terrain. So we have new publication coming soon. And yeah, so I would say it works on the rough terrain, but yeah, I think the publication will be out in a week, and you can probably watch there. And the problem is, so how many samples do we need to train policy like that, right? Of course, not that just that policy, but also more complicated policies. So the first example I gave was about 1 million samples. So this is just running forward. This was trained in 2 minutes. If you want to give a velocity command to the neural network, so the network is conditioned on the velocity command, it takes about 30 minutes and 10 to 100 million samples. And that's still not interesting. We want to port it to the real robot. So if we, I'm going to talk about it more later, but if we train on your actuarial network, which simulates the actuarial dynamics, we can put it to the real system, but it just takes a bit more time to converge. So then it's about 100 million to 1 billion. Of course, at 100 million, you see nice running, but it's constantly rising. The performance is constantly rising to 1 billion, then it's kind of settles down. And if you want to generalize this for different terrains, then we can get something like this. Right? So here, robot scans the environment. The robot knows, then figures out where to step. Then it places a foot there. And this is still end-to-end. So I'm not giving anything. I'm just giving the terrain scan, and the robot has to figure out everything from scratch, from the randomly initialized neural network. So, but in order to do this, we need 150 billion samples, right? 150 billion time steps. And if you use RISIM, this takes about 4 days to train. If you use other simulators like Pyblit, this will take 3 months to train. Right? So that's why I've been working so hard to make this fast simulator running. Oops. Yeah, so this is Ogre visualizer, and in the background we simulate the alien robot. Of course, you can simulate more, but not in the same not in the same world, right? So if you put them in the same world, then you have to check the collisions between the robots, and this is very time consuming. So if you create one robot for one world, then we can actually simulate more. But the point is, how can we compute the contact forces between the robots or between the robot and the ground? So if you see this image, you see the red dots, those are the contact points. And the key is how can we compute the contact impulse acting at that contact point. Physics engine? Yes, it's a physics engine. So I'm going to briefly talk about what we do in RISIM. So let's imagine that we have a robot, you throw a ball, they make a contact, and the contact point on the robot defined as A, and the contact point on the ball is defined as B. So we can define the relative velocity between the 2 points, which I write V impact. We can find the equivalent mass to be exact equivalent mass matrix, which is the impact mass. So here we find the inverse of the impact mass first. Then we just get the F equals ma equation. And this is your favorite dynamics equation. We just have to solve for that F equals ma. Of course, we have this K because there are other forces acting on it. And we have a gravity force, Coriolis force, and we also have a force from other contacts, right? Because that's not the only contact point, then the forces from other contact points. But I just put them together in one constant, I call this K, and we solve this F equals ma plus K equation. So if you're curious how to find this K, then also another person said this, but Dr. Roy Featherstone wrote a book on this. So if you're curious, you can buy the book and study. But yeah, that's not the point of this presentation. It's about finding this F equals ma plus some constant. If you multiply the dt on both sides, we get, instead of force, we get impulse. Instead of the acceleration, we get the change in velocity, right? So we started from this continuous dynamics, we approximated to this discrete dynamics, discrete time dynamics. Why do we do this? It's easier to solve. Right? That's the only explanation I can give. if you know more about this, of course, you can talk about the Paine paradox, but yeah, then this will take some time to explain what it is. The point is that it's easier to solve. So we have 6 equations for this F equals ma equation. We have, 6 variables, unknown variables in the equation. We have 3 equations, so we need 3 more constraints. So the constraints are listed here. We have complementarity condition, which states that the impulse times the velocity in z direction should be multiplied together. They should be 0. We have Coulomb's friction constraint, and we have a contact energy minimization criteria, right? So this is probably somewhat new to you, but this contact energy minimization is can be intuitive that your friction force is acting in the opposite direction of your velocity, which is the direction that minimize the energy dissipation, right? But since you are working in the discrete time space, you have a starting velocity and end velocity, so it's a bit hard to pick which one you want to go for. And I just use a minimization optimization. I just convert it to a optimization problem. Right? So this problem is quite nice because we have a unique solution to this problem. And yeah, this of course is nice for optimization problem. So I'm going to briefly talk about the geometry of the problem. So we have the zero velocity constraint of plane. So on this blue plane, we have zero velocity of the contact point has zero velocity, and it can be on this plane, either on this plane or at the origin. The origin means that the impulse is 0, right? So if either the impulse is 0 or the velocity is 0. Okay, it's very simple. Of course, if the impulse is 0, it's very easy to solve. It's actually easy to figure out if the impulse is 0 or not. So we focus on the on-plane problem. And you can see that this the green one defines the Coulomb's friction law cone constraint. Right? So I think everyone is familiar with this. There is a quadratic constraint that defines this friction cone, and that defines the ratio between the normal force and the tangential friction force. Okay, so all we have to do is do the minimization on this feasible set. And it's actually so we have 2 cases where the zero velocity case. So if the contact can completely remove the energy from the contact point, the solution will be inside the ellipse. And in this case, it's actually a linear problem. So this is not interesting. I mean, it's important, but it's easy to solve. The case we are interested in now is when the zero solution is outside, and then the optimal solution is on the boundary of the ellipse. Okay, so that's the problem that we are interested in. And we solve this using so by the way, this is a quartic problem. We can convert this problem to a quartic problem in terms of the x and y impulse. But quartic equation is actually hard to solve. There is an analytical solution, but you get multiple solutions. You have to check multiple conditions. But actually, we realized that for programming, this is quite bad because probably there is a bit of branching and so on. So this actually takes even longer than the numerical solution. So here what we do is we do iterative quadratic approximation to the criteria, and we converge to the optimum. So this idea is, of course, similar to the Newton's method, but it's not exactly Newton's method, the way we implemented it to make it more numerically efficient. So I'm preparing a publication on this, so you can probably read more on that publication. But anyway, so this method is there in Ryzen. You can enjoy the fast simulation just after downloading the simulator. So Ryzen works in Linux, Windows, Mac, and it works in C++, MATLAB, and Python. So you can pick your best combination or your favorite combination. RiceSim is faster than anything else out there. And actually it'll be a couple of order of magnitude faster than like OD or Gazebo. Right? So there is no surprise to, well, there's no reason not to use this over Gazebo. The reason that it's so fast is also because of a lot of code optimization that I put into. Of course, this code optimization is quite painful. You have to profile your code every time you change a bit, then profile. But that's what we did, and yeah, and that's why it's fast. So just introducing basic features, we can simulate robots. We can also simulate the constraints. We can simulate unilateral constraint, bilateral constraint. If it's unilateral constraint, we can also define the direction. We can also do the large scale height map. So this is just animal thrown in the air. It lands on this height map, and yeah, it's about 8 kilometer and 8 kilometer in dimension. It's a square height map. And also nice thing about the RiceSim is like one-to-one replacement for IBDL. You have like all the dynamics properties you can get. And you don't pay additional overhead for computing these dynamics properties, because in simulation, you just get them for free, and then you can just use it for your control. And using this simulation, so I'm going to talk about this our 2019 publication. So using this simulator alone is actually not enough. So we need to somehow model the dynamics of the actuator, right? Because I think I think Olivier mentioned that the dynamics of the actuator is quite complicated, and it's hard. It's very far from ideal. Right? So for the any drive, there was about 40 milliseconds of delay from peak to peak if you command the maximum step input. And of course, this is very hard for control point of view. So we trained a neural network for this actuator using supervised learning. And we found that it's actually quite easy to learn these dynamics using the neural network. You just have to provide a sufficient length of history to the network, because the current observable state is not sufficient to determine the output of the torque output, right? So we have to condition everything on the long history. But after we do that, yeah, it's quite accurate, as you see. So here, the red one is the learned model. The green one is the measured torque. This is not the train data. This is test data, right? So you can see that they're almost overlapping. So using this technique, so this is an open loop control, right? Of course, the robot, the controller aware of the joint position, but it's not aware of the position of the robot in global frame, right? So everything has to be the position of the robot has to be is open loop. It's not, there is no feedback loop, but it matches the reality quite well, right? And so even if we change the coefficient of friction, actually match quite well, because it doesn't slip, right? So this is somewhat simple case. So if it starts to slip, of course, the difference will be big. But yeah, for this kind of problem, it wasn't so hard to match the state distribution. So yeah, so this is some of the motions that we demonstrated in science robotics. Yeah, actually this is quite lagging. So I'm going to just play video one by one. So I think the top one you already watched. So on the bottom left, we have this standing up behavior. Yeah, we can train this stand-up behavior end-to-end. And we can also train a control policy for a quadrotor. So this is also end-to-end training. We throw a robot, and yeah. So also in simulation, we throw the robot, and it learns how to go back to the origin, the origin of the world frame. Okay. Yeah, that's all for my talk, and yeah, I'm happy to answer your questions.